Welcome to Science Bills. For all of human history, when we looked up at the moon, we basically saw this romantic, pristine silver sphere.
Yeah, it was a symbol, right? A poetic muse. Or just the untouchable heavens for early explorers.
Exactly. But if you shift your perspective right now, in the year 2026, and you put on a different set of lenses, like strictly industrial, cold economic lenses, that pristine sphere completely vanishes.
It really does. It just evaporates. I mean, the moment you understand what is actually buried up there, you stop seeing craters and, seas of tranquility.
Right.
The romance is just entirely replaced by pure calculating utility.
Yeah, instead of a celestial body, you look up and you basically see a 238,000-mile distant oil field.
Exactly.
You
Yeah.
see this massive high-stakes industrial zone just waiting to be tapped. It's an ultimate diagnostic shift in how humanity views space. We're looking at the raw economic engine of the next century.
And the absolute core of that shift is really simple. Whoever controls that dead rock in the sky, well, they control the baseload power grid down here on Earth.
Which is the exact mission of today's deep dive. We are going to look way past the carefully managed public relations campaigns about returning astronauts to the moon in 2026.
Yeah, looking past the flags and the footprints.
Right, past all the inspiring press conferences. Because we are here to uncover the real, raw reason that global superpowers and private billionaires are currently engaged in this breakneck race back to the lunar surface.
The real reason.
Exactly. The central thesis we're exploring today is that humanity is hunting for lunar helium-3 to power clean fusion reactors. And we're going to unpack these staggering, almost incomprehensible physical hurdles of mining, like 100 tons of lunar dirt an hour in a vacuum.
Which is a nightmare.
A total nightmare. And then we'll examine the intense geopolitical gold rush unfolding right now, primarily between the United States and China.
And to do that, we are synthesizing a really massive stack of intelligence for you today. We're pulling from the geopolitical mandates that are explicitly outlined in the newly passed U.S. Senate's NASA Authorization Act of 2026.
Which was a huge deal.
Massive. And we've got the highly technical, granular financial and engineering roadmaps from space mining startup.
Companies like Interloon, right?
Yeah, Interloon and Black Moon Energy Corporation. Plus, we're cross-referencing all of that ambition with foundational scientific papers detailing the actual physics of nuclear fusion and the precise, brutal mechanics of lunar extraction.
Okay, so to truly understand the billions of dollars being mobilized right this second, we really have to start at the foundation. We have to look at the basic science. What exactly makes this invisible gas, helium-3, the single most valuable substance in the entire solar system?
Well, it all comes down to its atomic structure
Oh, yeah.
and a kind of quirk of how our solar system operates. So let's start with the atom itself.
Okay.
Helium-3, or He3 as you'll see it in the scientific literature, is this incredibly rare, non-radioactive isotope of helium. Now, standard helium, the stuff you use to fill a party balloon or run a chemistry experiment, that's helium-4.
Got it.
It has 2 protons and 2 neutrons in its nucleus. But helium-3 is missing a neutron. It has 2 protons and just 1 single neutron.
So it's slightly lighter, structurally speaking.
Right. And because of that specific structural imbalance, it makes it the perfect puzzle piece for a very specific, incredibly powerful type of nuclear fusion. But here's the massive catch. It is virtually non-existent on Earth.
Wait, why is that? Because I thought helium is the second most abundant element in the universe. So why is this specific flavor of it missing from our planet?
Because our planet is heavily shielded. Earth is protected by a thick atmosphere and this massive, powerful global magnetic field.
Which is great for keeping us alive.
Exactly. It's great for us because it deflects the solar wind. And the solar wind is basically this continuous stream of highly energetic particles blasting out of the sun. But the solar wind is also the primary delivery mechanism for helium-3 in our solar system.
Oh, I see.
Yeah, so because our magnetic field bounces that wind away, the only helium-3 we actually have on Earth is created artificially in like microscopic amounts. We generate roughly 1 single kilogram per year globally.
1 kilogram a year.
Yes.
For the entire planet.
The entire planet. And it is strictly captured as a byproduct of tritium decay.
Yeah.
During the routine maintenance of our nuclear weapons stockpile.
Wow.
Yeah, so it's an incredibly scarce, artificially hoarded resource. But if you look at the moon...
The moon has no atmosphere.
Right, no atmosphere, no global magnetic field. It is completely naked to the cosmos. So for over 4 billion years, the solar wind has just been relentlessly blasting the lunar surface.
Baking it.
Exactly, directly embedding these high-energy solar particles into the very top layer of lunar dirt, which scientists call the regolith. And because of this uninterrupted bombardment, planetary geologists estimate the moon holds an inventory of somewhere between 1 to 5 million metric tons of helium-3.
That is a staggering discrepancy. Earth has 1 single kilogram, and the moon has up to 5 million tons just sitting right on the surface. So what does this gas actually do? You mentioned it's the perfect puzzle piece for fusion, but walk us through the actual physics here. Why is this specific isotope the holy grail for energy?
Okay, to appreciate the helium-3 advantage, you really have to look at the massive problem with traditional fusion research. For decades, scientists have been trying to achieve fusion using what's called a deuterium-tritium reaction, or DT fusion.
Which involves smashing heavy isotopes of hydrogen together, right?
Exactly, smashing two heavy isotopes of hydrogen together. And it definitely works. I mean, we've seen it work in test reactors, but it is incredibly messy from an engineering standpoint.
How?
Well, when you fuse deuterium and tritium atoms together,
Right.
the reaction produces an immense amount of energy, sure, but it also ejects these highly energetic neutrons.
And a neutron, by definition, has no electrical charge. Why is that a problem inside a reactor?
Because you can't control it with magnets. Inside a fusion reactor, you're containing plasma that is literally hotter than the center of the sun.
Right.
And you contain that plasma using incredibly strong magnetic fields. It's basically a magnetic bottle. But because neutrons have no charge, they just ignore the magnetic bottle completely. They fly right through it and smash violently into the physical steel walls of the containment vessel.
So they act like microscopic high-speed bullets.
Exactly like billets. And over time, this intense neutron bombardment physically degrades the structural integrity of the reactor walls. It makes the metals super brittle. Plus, it irradiates those surrounding materials, which creates radioactive waste.
So even though fusion is supposed to be the clean alternative to traditional nuclear power, this specific DT fusion still creates a radioactive mess.
It does. It's significantly less waste than traditional nuclear fission, which is what current nuclear power plants use. But it's still a dangerous, highly problematic byproduct. It requires immense shielding, constant maintenance, and, long-term disposal strategies.
Right, so where does helium-3 come in?
Well, let's swap out the fuel. If you replace the radioactive tritium with the lunar helium-3, you now have a deuterium-helium-3 reaction.
Yeah.
The fundamental physics equation changes. Deuterium plus helium-3 yields a helium-4 atom, a proton, and 18.3 megaelectron volts of energy.
Okay, so a proton instead of a neutron. What is the real-world engineering translation of that shift?
The real-world translation is that this new reaction is what physicists call neutron poor. Instead of throwing off these destructive neutral particles that smash your reactor to pieces, it primarily yields positively charged protons.
And protons have a positive electrical charge.
Right. So they do interact with magnetic fields. We can use those exact same magnetic fields that contain the plasma to literally catch the protons, slow them down, and directly convert their kinetic energy into electricity.
Okay, let me see if I'm grasping the magnitude of this. With traditional nuclear fission plants today, we're basically just splitting atoms to generate heat, right?
Right.
And we use that heat to boil water, create steam, and the steam physically spins a giant mechanical turbine to make electricity.
That's entirely correct. Fission is, at its core, just a highly sophisticated, incredibly dangerous way to boil water.
With the traditional DT fusion we've been trying to build, the one with the destructive neutrons, we're basically doing the exact same thing. We use the heat from the fusion plasma to heat a blanket of liquid metal, which boils water, which spins a steam turbine. It's like a wildly powerful, high-pressure, borderline uncontrollable steam engine.
Yeah, it works, but it has all these volatile moving parts and thermal losses. You are still bound to the thermal cycle. You lose massive amounts of efficiency just transferring heat from one medium to another.
But with helium-3 fusion, because you're catching charged protons with magnets, you bypass the thermal cycle entirely. I don't need to boil water. You don't need a steam turbine. It's like jumping straight to a perfectly clean direct drive electric motor.
That is a brilliant analogy. You are eliminating the mechanical middleman. You bypass the thermal cycle. You do it safely. And crucially, you do it without creating the radioactive footprint that degrades the reactor.
Wow.
And the energy density of this direct drive motor is almost incomprehensible to the human mind. Let's ground this in some real numbers to understand the economics. Just 100 kilograms of helium-3 could entirely power a city the size of Seattle for an entire year.
Just 100 kilos.
Yeah. And if you extrapolate that out to a national scale, just 25 metric tons of this gas could power the entire United States grid for a year.
25 tons. I mean, you could fit the annual energy consumption of the entire United States into the cargo bays of a couple of commercial semi-trucks. That is staggering.
It really is.
But let's look at the immediate near-term value, because commercial baseload fusion reactors aren't plugged into our grids today. Is there an immediate market for this gas, or is this entirely a long-term play?
Oh, there's an incredibly urgent, immediate market. The sources we're reviewing show that helium-3 is absolutely critical for quantum computing right now.
Really? How so?
Well, quantum computers require hardware called dilution refrigerators. These machines are designed to keep the quantum bits, or qubits, stable at temperatures hovering just a fraction of a degree above absolute zero.
So extremely cold.
Insanely cold. And to achieve that kind of deep freeze, you have to mix liquid helium-3 and liquid helium-4. The way those two isotopes interact at a quantum level actually absorbs ambient heat, plunging the whole system into an ultra-cold state. Without helium-3, the dilution refrigerator doesn't work. And without the refrigerator, the quantum computer completely destabilizes.
And it's also vital for medical imaging, right? The sources mention high-precision MRI scans.
Yes, specifically for advanced lung scans. If a patient inhales polarized helium-3 gas, it acts as an incredibly precise contrast agent. Now, normal MRI machines are tuned to detect water in your body, which is why they are great for imaging tissues, but terrible for imaging the lungs.
Because lungs are mostly empty space and air?
Exactly. But when you inhale helium-3, the MRI can perfectly map the exact real-time ventilation dynamics of the lungs, which is vital for treating severe respiratory diseases. So you basically have the two most advanced fields of modern technology: quantum computing and advanced medical diagnostics, entirely reliant on a gas that Earth produces 1 kilogram of per year.
Which makes that terrestrial supply chain incredibly fragile. I actually want to bring up the geopolitical shockwave that hit the markets recently. Let's talk about February 2026 and the Strait of Hormuz, because this is where the theoretical economics smashed into real-world geopolitics.
This is a vital data point. In February 2026, severe military tensions and naval operations forced a temporary closure of the Strait of Hormuz.
Right.
And the immediate consequence was that it completely choked off terrestrial helium supplies coming out of Qatar, because Qatar is a massive global supplier of helium, capturing it as a byproduct of their natural gas extraction. Almost overnight, global spot prices for helium spiked over 50%, hitting $1,200 per 1,000 cubic feet.
I imagine if you were running a hospital that month or managing a multi-billion-dollar quantum research lab, you were suddenly facing the very real prospect of rationing your operations.
Yeah, exactly. And what's fascinating here is how this specific supply shock altered the psychology of the global markets. It proved to investors and governments that lunar extraction is no longer just some futuristic sci-fi dream. It has become a pressing, immediate economic necessity.
So it woke people up.
Yeah. The semiconductor industry, the quantum computing sector, the medical field, they all suddenly realized their entire supply chain, the bedrock of their technological edge, could be held hostage by terrestrial geopolitics. A naval blockade on Earth can cripple a quantum lab in California.
Wow.
That realization is why helium-3 currently commands a projected price of up to $20 million per kilogram.
Wait, I have to step in here and challenge the timeline on this. $20 million a kilogram is an insane valuation, yes. It makes sense for MRIs and quantum computers. But the real volume, the millions of tons we are talking about mining, is for energy. And commercial fusion energy is still largely theoretical, isn't it? We are talking about private companies and sovereign governments preparing to spend hundreds of billions of dollars to build a logistical supply chain to mine fuel for engines that literally do not exist commercially yet.
Yes.
That sounds like the worst venture capital pitch of all time. Why take that risk now?
It's a completely valid challenge. And it's the exact question every major investor asks. But to understand the timing, you have to look at the development curve of magnetic containment technology. It is rapidly, exponentially catching up to the fuel requirements.
Okay.
The fusion reactors themselves are moving out of the realm of theoretical physics and into applied engineering. For instance, look at the recent breakthrough from Commonwealth Fusion Systems out of Massachusetts. They recently proved they could create a 20 Tesla magnetic field.
Okay, for those of us who don't measure things in Teslas, how strong is that?
To give you a sense of scale, the magnetic field of the Earth, which protects us from the solar wind, is measured in fractions of a single 1/10,000th of a Tesla. A typical junkyard magnet that lifts whole cars is about 1 Tesla.
Okay.
A clinical MRI machine is usually around 1.5 to 3 Teslas. Commonwealth Fusion created a 20 Tesla field. The outward pressure generated by a magnetic field that strong is roughly equivalent to the physical pressure at the bottom of the Mariana Trench.
So they essentially built a magnetic cage strong enough to hold the pressure of a miniature star.
Precisely. And they achieve this using high-temperature superconducting electromagnets, specifically YBCO tapes, yttrium barium copper oxide. The ability to magnetically contain the volatile plasma required for these reactions is no longer the insurmountable hurdle it was 20 years ago.
So the tech is there.
The bottleneck is shifting. It is no longer just the reactor physics. The bottleneck is entirely the fuel supply.
Yeah.
The entities racing to the moon right now are making a highly calculated multi-decade bet. By the time they can successfully establish a reliable, high-volume lunar supply chain in the mid-2030s, the commercial fusion reactors will be coming online globally.
And they will be desperate, starving for fuel.
That is the exact strategic gamble. The mining tech and the fusion tech are on parallel tracks, scheduled to collide in the next decade.
So let's explore the reality of that gamble, because we just connected the staggering, world-changing value of this fuel to the economic models, but now we have to face the sheer terrifying physical reality of trying to extract it. We are talking about pulling an invisible gas from a dead, irradiated rock 238,000 miles away. How brutal is the math of lunar mining?
The math is punishing. You have to remember how the helium-3 got there. It wasn't formed geologically. It was deposited by the solar wind over billions of years. That means it is incredibly diffuse. It's not sitting in concentrated, high-density veins like gold or silver or coal on Earth. You can't just find a helium-3 mine and dig a shaft.
So how spread out is it?
According to planetary scientists like Ian Crawford, who has modeled this extensively, the highest concentrations ever observed in Apollo lunar samples are only about 10 parts per billion.
10 parts per billion? That sounds almost negligible.
It is microscopically sparse. And that's the absolute maximum. The average concentration across the lunar surface is closer to 4 parts per billion.
Let me try to visualize what 4 parts per billion actually means for an industrial operation. If I want to harvest just 1 single kilogram of helium-3, the amount that fits in a small cylinder, how much lunar dirt do I have to process?
To get 1 kilogram of helium-3, assuming a perfect 100% extraction efficiency, you have to physically excavate, process, and sift through 500,000 metric tons of lunar regolith.
500,000 tons of soil for 1 kilogram.
Let's put that physical volume into perspective. You are essentially strip mining a 20-acre plot of land to a depth of 10 feet, or about 3 meters. You are excavating an entire suburban neighborhood's worth of deep soil, processing every single grain of it, all to yield an amount of gas that you could comfortably fit inside a standard school backpack.
That sounds like a logistical nightmare on Earth, let alone in the vacuum of space. And the process itself isn't just moving dirt from point A to point B, is it? It's not just a bulldozer. How do you actually get the gas out of the rock?
The extraction sequence is highly energy intensive. First, you have to dig up the soil, then you have to sort it mechanically, because the helium-3 is primarily trapped in the absolute finest grains of the regolith grains, smaller than 50 microns.
Okay, so you sift it.
Once you've sifted the fine powder from the larger rocks, you have to heat it. You have to bake this dirt in an enclosed furnace to 600 degrees Celsius. That's 11,112 degrees Fahrenheit.
Why that specific temperature?
Because that is the thermal threshold required to fracture the molecular bonds, trapping the solar wind volatiles inside the regolith. At 600 degrees Celsius, the dirt essentially exhales the trapped gases. But it exhales everything: hydrogen, standard helium-4, carbon compounds, and the helium-3.
So it's all mixed together.
Yeah, so then you have to run that mixed gas through a highly complex separation plant to isolate the helium-3. Finally, you have to use cryogenics to supercool that specific isotope into a liquid state and store it in heavily pressurized, double-walled containers for the trip back to Earth.
And just to remind ourselves, you have to do every single step of that process in a hard vacuum, bathed in deadly cosmic radiation in 1/6 Earth gravity.
Right, and this brings us to the actual engineering solutions being developed right now to solve this nightmare. You mentioned the private sector earlier. Let's look at the company leading the mechanical charge here, which is Interloon.
The Seattle-based startup.
Yes, and their pedigree is serious. It was founded by former Blue Origin executives Rob Meyerson and Gary Lai, along with Apollo 17 astronaut Harrison Schmitt.
Harrison Schmitt. It's vital to note that out of all the Apollo astronauts, Schmitt was the only actual trained geologist to ever walk on the moon. He spent days physically interacting with this dirt. He knows exactly how it behaves.
His firsthand experience is the absolute bedrock of their engineering approach. Interloon is currently developing a machine called the SILT excavator. SILT stands for Scalable Implement for Lunar Trenching.
Okay.
And they aren't trying to build this alone at a vacuum. They've partnered with Vermeer, which is a massive, highly experienced, heavy industrial equipment manufacturer here on Earth, along with the mining experts at the Colorado School of Mines.
So this isn't just a science experiment.
No, this is not a delicate, slow-moving scientific rover like Perseverance on Mars. This machine is designed to be a beast. It is engineered to ingest and process 100 metric tons of moon dirt per hour.
Wait, how does a machine mechanically dig up 100 tons of dirt an hour in 1/6 gravity? I'm picturing the physics here. If you have a massive excavator on Earth, it uses its own sheer weight to force the shovel down into hard, compacted soil, right?
Yeah.
If an excavator on the moon only weighs 1/6 of its Earth weight, wouldn't pushing a shovel into compacted dirt just lift the machine itself off the ground?
You've hit on one of the most notoriously difficult problems in lunar engineering. It's the traction and mass problem. If your machine is too light, the equal and opposite reaction of digging just pushes you away from the surface.
Yeah, like trying to dig while floating.
Exactly. To solve this, lunar excavators either have to be incredibly massive, which makes them prohibitively expensive to launch, or they have to use entirely different digging mechanics. Instead of brute force scooping, engineers look at percussive digging, counter-rotating bucket wheels that cancel out the lifting forces, or even anchoring systems that physically pin the machine to the bedrock while it works.
So they are essentially rethinking heavy industry from the ground up. But let's talk about the power required for this. How do you power an operation that not only digs up 100 tons of dirt, but heats 100 tons of dirt to 600 degrees every single hour?
It's a massive challenge.
Especially when you factor in the lunar environment, because the lunar night lasts for 14 continuous Earth days. And during that darkness, the ambient temperatures plunge to negative 150 degrees Celsius. Solar panels aren't going to cut it for half the month.
The thermal and energy demands are colossal. During the 14-day lunar day, you can rely on massive, deployable 60-kilowatt solar arrays to run your heating elements and separation plants.
Yeah.
But to survive the 14-day night and to keep operations running, because downtime at an industrial facility ruins the economic model, batteries simply lack the energy density at this massive scale.
You'd need too many batteries.
Way too many. You cannot haul enough batteries to the moon to heat thousands of tons of dirt for 2 straight weeks. You have to bring in nuclear fission.
We are putting fission reactors on the moon.
Yes. The designs call for small, modular fission reactors. And you can't just leave them sitting out on the surface. They have to be buried deep underground or covered under massive radiation berms built by the very excavators doing the mining to protect the human operators and sensitive electronics from the reactor's radiation.
So we have machines operating in 1/6 gravity, cycling between extreme heat and extreme cold, powered by buried nuclear reactors. That sounds difficult enough. But I've read the source material from the Apollo missions, and the temperature swings aren't even the worst part of operating on the moon. The absolute worst, most destructive element is the dust itself.
Oh, the regolith is an engineer's worst nightmare. Lunar dust is absolutely nothing like Earth dust.
Because Earth dust has been weathered.
Exactly. On Earth, wind and water constantly erode sand and dirt over millions of years, tumbling the particles until they are relatively round and smooth. Lunar dust has never been weathered. It was created by billions of years of micrometeorites slamming into the bedrock at thousands of miles an hour.
Just constant impacts.
Yeah, and these impacts vaporize the rock, which instantly cools in the vacuum of space, forming microscopic, highly irregular shards of glass.
So it's not dust, it's a powder made of razor blades.
It is entirely abrasive. And because there is no atmosphere to insulate it, the constant bombardment of the solar wind leaves the dust highly electrostatically charged. It literally clings to everything through static electricity.
Oh, wow.
During the Apollo missions, it coated the astronauts' visors, it degraded the seals on their spacesuits in a matter of days, and when they got back in the lunar module, it smelled like spent gunpowder.
I imagine that electrostatic glass powder does terrible things to heavy machinery.
It is catastrophic for machinery. It works its way into mechanical joints, it bypasses rubber seals, and it grinds down gears and bearings like industrial sandpaper. Furthermore, because you are in a vacuum, you can't use traditional liquid lubricants like oil or grease.
They just boil or freeze, right?
Exactly. They would instantly boil off or freeze solid. So, engineering an excavator that can reliably ingest 100 tons of abrasive, statically charged glass every single hour without completely destroying its own internal mechanics is arguably one of the greatest tribological and mechanical challenges of our time.
we've established the what and the incredibly brutal how. The sheer scale of the engineering is mind-bending. But someone has to pay for this. If we step away from the engineering schematics and look at the massive flow of global capital, it's clear the private sector is not waiting around for governments to figure this out.
No, the money is moving right now.
Let's look at the private sector vanguard and the orbital infrastructure they are desperately trying to build.
The capital flow tells a very clear, urgent story. Investors aren't looking at this as a 50-year science experiment. They expect returns in the next decade. Look back at Interloon. They recently secured $18 million in an initial seed funding round, and they quickly followed that up with another $5 million in a safe round.
For those of us who aren't deeply embedded in Silicon Valley venture capital, what exactly does a safe round mean in this context?
SAFE stands for Simple Agreement for Future Equity. It's an investment vehicle designed for very early-stage startups. Essentially, investors give the company cash immediately without having to negotiate exactly what the company is currently worth. In return, the investors get the right to equity in the future once the company is properly priced in a larger funding round.
Okay, got it.
The fact that sophisticated space investors are throwing millions into a safe round for a lunar mining startup shows an intense appetite for risk. They are rushing to get their foot in the door because they believe the eventual upside is astronomically high.
And Interloon isn't just taking this money to build CAD models, right? They have a hard physical deadline approaching. In July 2026, they are launching hardware to the moon. They've built a specialized multispectral camera that will fly on Astrolab's FLIP rover.
Right, and this isn't just a generic camera to take pretty pictures of craters. This specific instrument was co-developed with NASA's Ames Research Center. Its sole operational purpose is to scan the regolith and varying wavelengths of light to map out the chemical signatures of the soil. They are hunting for those elusive, high-concentration helium-3 hotspots.
They are prospecting.
Exactly, they are prospecting.
And they already have buyers lined up for the gas they haven't even mined yet. The sources show they signed a $300 million deal to supply 10,000 liters of lunar helium-3 annually to a company called Blue Force, starting in 2028 and running through 2037.
Blue Force is a massive, critical player in the quantum tech space. They're the ones who build the advanced cryogenic systems, those dilution refrigerators we discussed earlier. So from a business perspective, the demand side of the equation is entirely locked in. The customers are waiting with open checkbooks.
Then you have competing entities like Black Moon Energy Corp. Or BMSC. Their corporate literature is incredibly aggressive. They are launching robotic missions not just to scientifically map the moon, but to gather what they explicitly call decision quality data.
Yeah, they're moving fast.
They are building complex financial models to prove that lunar helium-3 will actually undercut the levelized cost of energy of terrestrial power plants.
That's a crucial metric. Levelized cost of energy, or LCOE, is how the energy industry compares apples to oranges. It calculates the total lifetime cost of building, operating, fueling, and decommissioning a power plant, divided by the total energy it will produce.
Okay.
BMSC is arguing that while the upfront cost of establishing a lunar mine and transporting helium-3 is incredibly high, the fusion reactors themselves require near-zero maintenance. They produce zero waste that requires expensive long-term geological storage, and they operate with massive efficiency.
So long-term, it pays off.
Right. When you stretch that out over a 40-year lifespan, they argue the LCOE of lunar fusion will actually be cheaper per megawatt hour than burning natural gas or building traditional fission plants.
That is a wildly bold claim. But here is the massive catch hanging over all of these financial models. The supply chain to make this happen literally does not exist yet. It has to be built entirely from scratch. You can't just launch a rocket, land on the moon, grab a bag of dirt, and fly straight home.
The physics of orbital mechanics won't allow it.
Right. You have to build an elaborate hub-and-spoke orbital logistics network.
And if we connect this specific mining goal to the bigger picture of orbital infrastructure, the Lunar Gateway is the absolute linchpin of this entire network.
Tell us about the Gateway.
The Gateway is a modular space station, but unlike the International Space Station, which orbits just above Earth, the Gateway is positioned in what's called a near-rectilinear halo orbit, or NRHO, around the Moon.
Why a halo orbit? Why not just orbit it in a flat circle around the Moon's equator?
A near-rectilinear halo orbit is an incredibly stable, highly elliptical path. It brings the station very close to the lunar North Pole and then swings it far out over the South Pole. This specific geometry has two massive advantages.
What are they?
First, it requires very little fuel to maintain the orbit, so the station can stay there for decades. Second, it ensures the station has a constant, uninterrupted line of sight to Earth for communications while providing a perfect vantage point over the lunar South Pole, which is where all the action is going to be.
Because of the water.
Exactly.
Mm.
NASA actually powered on the Gateway's Power and Propulsion Element, the PPE, in early 2026. This station will act as the crucial orbital way station. It's the central hub where fuel, supplies, and eventually harvested helium-3 can be stored safely, transferred out of the lunar gravity well, and loaded onto Earthbound transport vessels.
But the gateway is just a transfer station. The actual vehicles moving between the gateway and the lunar surface face an absolute monster of a hurdle, and that is the orbital propellant depot problem. Let's look at SpaceX, who holds the contract for the human landing system.
It's a massive challenge.
Right. To land something the size of SpaceX's Starship on the moon, it requires an obscene amount of fuel. The ship is so massive that it burns almost all of its fuel just getting out of Earth's gravity. So to get it to the moon, they have to launch a dedicated empty fuel depot into Earth orbit. And then they have to launch between 10 to 15 separate, fully loaded tanker flights just to fill that orbiting depot with cryogenic liquid methane and liquid oxygen.
It's a huge logistical train.
Only then can the actual lunar Starship dock with the depot, fill its tanks in orbit, and head to the moon.
And that orbital refueling process is arguably the highest risk technical element of the entire Artemis architecture. We have that critical NASA and SpaceX test scheduled for June 2026, where they will attempt to transfer 5 metric tons of cryogenic propellant between 2 ships in microgravity.
To a layperson, that sounds simple. Dock 2 ships, attach a hose, and pump the gas. Why is transferring fuel in zero gravity considered a make-or-break test?
Because fluid dynamics in microgravity are a nightmare. On Earth, gravity pulls liquid to the bottom of a tank, and the empty space, the gas, sits at the top. You put a pump at the bottom, and it reliably draws liquid.
Right. Gravity does the sorting.
But in microgravity, surface tension dominates. The liquid doesn't pool at the bottom. It clings to the walls of the tank, or floats in massive, chaotic, spherical blobs right in the middle. The gas bubbles mix intimately with the liquid.
And if you accidentally pump gas into a rocket engine instead of liquid?
The engine cavitates. It loses thrust instantly, the turbo pumps overspin, and the engine violently tears itself apart. It's a catastrophic failure.
So how do they force the fluid to behave?
They have to use what are called ullage motors. These are very small thrusters on the outside of the ship. Right before they start pumping the fuel, they fire these small thrusters to accelerate the ship slightly forward.
Creating a little bit of gravity?
Exactly. It creates a tiny amount of artificial gravity, just enough acceleration to force the floating liquid methane to settle firmly at the bottom of the tank over the intake valves. Doing this with highly volatile, supercooled cryogenic fluids without the heat of the pumps boiling the liquid into gas is insanely difficult.
Wow.
If SpaceX cannot flawlessly master this microgravity transfer in 2026, the Starship cannot physically reach the moon, period, let alone return with a cargo hold full of helium-3.
Which brings up the incredibly fragile nature of this entire economic plan. If a single Starship needs 15 separate rocket launches just to refuel it enough to reach the moon once, aren't the sheer launch costs going to completely wipe out that $20 million per kilogram profit margin for the helium-3? I mean, rockets are expensive.
It is the most critical bottleneck in the entire economic model, and the companies know it. Currently, heavy lift launch costs hover anywhere from $1,500 to $10,000 per kilogram just to reach the lunar surface, depending on the vehicle. At those prices, the math is incredibly tight, even for a product as valuable as helium-3.
So how do they make the math work?
The only way the financial models work long-term is through 2 indispensable factors. First, full and rapid reusability of the launch vehicles. SpaceX and Blue Origin are pushing heavily toward rockets that operate like commercial airliners, landing, refueling, and taking off again in days, spreading the capital cost over hundreds of flights.
And the second factor?
The second factor is even more important. It is the absolute holy grail of space exploration, in situ resource utilization, or ISRU.
Which essentially means living off the land, using the raw lunar resources to manufacture the rocket fuel for the return trip, rather than dragging every single drop of fuel all the way from Earth.
Precisely. The physics of the rocket equation are unforgiving. If you have to haul your heavy return fuel out of Earth's massive gravity well, lug it 238,000 miles and land it softly on the moon just so you can use it to fly back, you go bankrupt. The payload penalty is too high.
It's just too much weight.
Right. But if you could manufacture your return fuel on the moon, the profit margins explode, because your ships arrive empty and leave full.
So we have private companies taking immense existential financial risks to build these mining excavators and orbital gas stations. But they aren't operating in a vacuum, no pun intended. They are heavily backed, subsidized, and protected by global superpowers who have entirely different, deeply strategic motives.
Geopolitics are driving everything right now.
Exactly. This brings us right to the geopolitical chessboard. Let's look at the geopolitical gold rush unfolding between the United States and China. Because the tone of the geopolitics in 2026 has shifted dramatically.
We are no longer talking about the peaceful scientific exploration of the Apollo era. The language has shifted to securing strategic dominance. Look at the U.S. Senate. They unanimously passed the NASA Authorization Act of 2026.
Unanimously.
Yes, and note the unanimity. In a deeply divided political climate, a unanimous vote is exceedingly rare, and the language codified in the bill is unprecedented. It explicitly calls for a permanent operational lunar surface moon base by 2030.
Senator Ted Cruz was extremely vocal about this during the hearings. He framed this mandate not as scientific curiosity, but as an urgent strategic necessity. He stated clearly that space dominance will define global power in the 21st century.
It's a massive shift.
It really is. I mean, when a superpower mandates a permanent industrial base on another celestial body, it's a land grab. Plain and simple.
And China is responding in kind, with equal urgency and immense resources. They are aggressively advancing their own architecture, the International Lunar Research Station, or ILRS, in a tight partnership with Russia.
What's their timeline look like?
In 2026, China's Chang'e 7 mission is actively mapping the lunar South Pole from orbit, dropping probes, and analyzing the terrain. Furthermore, their state-backed scientific institutions, specifically the Beijing Research Institute of Uranium Geology BRIC, are openly evaluating the exact parameters for helium-3 extraction.
So they are actively planning for it too.
Yes, they are publishing papers studying exactly how the isotope is fixated in the lunar soil and how to extract it most efficiently. They are not hiding their intentions.
Okay, I have to ask about the legal reality of this. If the U.S. and China are both aiming to set up massive mining operations, who exactly gives them the permit? Because the 1967 Outer Space Treaty, which both nations signed, clearly forbids any national appropriation of the moon.
Right.
You legally cannot plant a flag, claim a crater, and declare it sovereign territory.
That is correct. You cannot claim national sovereignty over the physical land. But the legal framework that held for 50 years is currently fracturing under the weight of commercial reality. To navigate around the 1967 treaty, the United States led the creation of a new framework called the Artemis Accords.
And a lot of countries have signed that, right?
As of 2026, 61 nations have signed on. The Accords introduce a highly controversial legal concept called safety zones. The idea is that if a commercial entity, say Interloon or SpaceX, sets up a massive, dangerous mining operation, they can officially declare a safety zone around their equipment to prevent harmful interference from other actors.
Let me make sure I understand the nuance here. I can't claim that I own the land, but I can claim the legal right to not be bothered, approached, or interfered with while my massive robots dig up all the valuable dirt on that land.
Exactly. You don't own the property. You own the exclusive operational rights to the area your safety zone covers. And to provide an impartial look at the intense tension this is causing globally, Church, critics, particularly international legal scholars, argue that these safety zones are nothing more than de facto territorial claims.
Like a legal loophole.
It's a brilliant legal loophole. You achieve the economic benefits of sovereignty without violating the letter of the 1967 treaty. China and Russia have vehemently declined to sign the Artemis Accords, viewing them as a U.S. hegemonic tool. Instead, their ILRS framework acts as a sovereign-centric counterweight to the U.S.'s commercial-heavy framework.
And the specific battlefield where these two massive legal and physical frameworks are currently colliding is the lunar South Pole. Specifically, they are both targeting the Shackleton and Newell craters. Why there? Why is everyone ignoring the vast flat plains of the lunar equator and racing to the jagged, dangerous South Pole?
Because of the shadows. The moon's axis is barely tilted compared to Earth's. At the lunar poles, the sun stays incredibly low on the horizon, just scraping the landscape. Because of this, the bottoms of deep craters like Shackleton and Nobel contain permanently shadowed regions, or PSRs.
So they never see the sun?
Never. These deep crater floors haven't seen a single photon of sunlight in billions of years. The temperatures inside these shadows plunge to -200 degrees Celsius. They act as massive, inescapable thermal traps.
And what's trapped inside?
Over billions of years, any comet or asteroid containing water that hit the moon eventually had its water vapor migrate and freeze solid inside these dark craters. Inside those shadows lies billions of tons of ancient water ice.
And whoever controls the water, ice, controls the fuel. As we establish, you absolutely need in situ resource utilization to make the economics of spaceflight work. You can't bring your fuel from Earth. But if you have ice, you can melt it, purify it, use solar power to run electrolysis, and split the H2O into pure liquid hydrogen and pure liquid oxygen, which is literal rocket fuel.
It is the highest grade rocket propellant we have. So the South Pole isn't just an interesting science destination for geologists. It is the absolute strategic high ground of the 21st century. It is the only gas station in the inner solar system.
Incredible.
If you control the ridges above the craters for constant solar power and the ice down below for fuel, you dictate the terms of the entire cislunar economy.
Which perfectly explains the military posture we are seeing, the race to resilience, as they call it. The U.S. Space Force's budget hit a massive $40 billion in 2026. The military is rapidly developing what they term space domain awareness tools.
Yes, the military presence is expanding rapidly.
For example, there's a highly classified autonomous vehicle program called the Jackal, which is meant to actively monitor cislunar space, that massive void between Earth and the Moon. And there's the Golden Dome Missile Defense Initiative, which places advanced sensors in high orbits to track hypersonic threats moving unpredictably through the atmosphere.
What's truly fascinating and somewhat alarming to geopolitical analysts is the intense blurring of lines between civilian commerce and military infrastructure. You have these ostensibly purely commercial mining startups, but they are receiving massive direct government defense contracts.
Oh, really?
Yes. Interloon, for instance, received a $1.25 million contract from the Air Force's AFWER-X program, which funds commercial innovation for military application, specifically to work on their helium-3 separation technology. They've also received grants from the Department of Energy.
So, if the Air Force is funding the mining tech, and the Space Force is patrolling the shipping lanes with autonomous vehicles like the Jackal, and China is landing dual-use sovereign hardware right next to U.S. commercial safety zones at the South Pole, we are effectively militarizing the supply lines for global energy.
It definitely looks that way.
How do we ensure this doesn't simply turn the moon into a heavily contested combat zone? Aren't we just exporting the Cold War to orbit?
It is a highly precarious situation. And exporting the Cold War is a very apt description. We are officially entering what geopolitical analysts call a multipolar orbital order. Because no single nation can legally claim territory and draw borders, commercial entities act as proxies for national interests.
That makes sense.
The military ensures the commercial supply lines remain open and secure. And the commercial entities secure the raw resources the military and the national grid desperately need to function. The classic deterrence theory that kept the peace between nuclear powers on Earth is currently, in real time, being adapted to the vacuum of space. It relies entirely on mutually assured economic destruction if anyone acts aggressively.
That is a terrifyingly fragile piece. But while helium-3 is the ultimate prize, the $20 million a kilo jackpot that makes all this risk worthwhile, it's not the only resource. To survive long enough to mine the helium, humanity has to learn to literally live off the land.
We have to.
This necessity is opening up an entirely new secondary orbital economy. Let's explore how we actually build a civilization up there.
We touched on the water ice at the South Pole earlier. Water truly is the blue gold of the moon. You need it for rocket fuel, but you also need it to keep human operators alive. To pinpoint exactly where this ice is and how deep it's buried, NASA is sending the Viper rover.
Viper stands for the Volatiles Investigating Polar Exploration Rover, right? I remember this mission was actually fully canceled in 2025 due to budget constraints, but it was saved after a massive outcry from the planetary science community.
Yes, the scientific and strategic community realized we were flying blind without it. Viper is now fully reinstated and scheduled to fly on Blue Origin's Blue Moon Mk1 lander in 2027.
What does the rover actually do?
It's an incredibly sophisticated machine. It uses a neutron spectrometer to peer up to a full meter underground as it drives through the pitch-black shadows of the Noble crater, actively hunting for the highest concentrations of that ice.
So once Viper finds the ice and we secure the water for life support and fuel, we need shelter. You can't just pitch a Kevlar tent on the lunar surface when microscopic micrometeorites are flying around at 10,000 miles an hour, not to mention the lethal solar radiation flares. We have to build hardened infrastructure.
Right. And hauling steel beams and concrete from Earth is economically impossible due to launch costs. So we turn to the regolith again. Using a process called sintering, engineers plan to use specialized microwaves or highly concentrated solar energy mirrors to literally melt the lunar soil in place. By melting and fusing the regolith, you can use massive 3D printers to extrude it like hot plastic.
Building igloos out of melted glass, essentially.
Exactly. You can 3D print thick, dense, radiation-shielding habitats for the crews. Even more critically in the short term, you must 3D print solid landing pads.
Why are landing pads a priority? Can't the rockets just land on the flat dirt like the Apollo lunar modules did?
The Apollo modules were tiny. When a massive 100-ton vehicle like the Starship fires its main engines just feet above the lunar surface, the exhaust plume is so violently powerful it acts like a massive sandblaster.
Oh, because of the dust we talked about.
Exactly. It kicks up that razor-sharp lunar dust at supersonic speeds, firing it into orbit where it can shred nearby satellites, or blasting it laterally where it will destroy any habitats or solar panels within miles. You have to melt the dirt into a solid, smooth landing pad just to safely arrive without destroying your own base.
So the moon becomes a heavy construction zone, but the orbital economy extends back toward Earth, too. It's not just about surviving on the moon, it's about utilizing the environment of space itself. Low Earth orbit, or LEO, is rapidly becoming the new high-tech factory floor for humanity.
Yes, and this is entirely driven by the unique physics of microgravity. When you manufacture materials on Earth, you are constantly fighting gravity. Gravity causes convection hot fluids rise, cold fluids sink. Gravity causes sedimentation heavier elements settle at the bottom of a mixture.
Right.
In the microgravity of orbit, convection and sedimentation completely disappear. Fluids mix perfectly. Crystals grow uniformly in all directions. You can create structurally perfect materials that are physically impossible to manufacture on Earth.
I know one of the major commercial pushes right now is for specialized fiber optics. Z-bland glass, right?
Z-bland is the prime example. It's a highly complex heavy metal fluoride glass. On Earth, when you melt the components to make Z-bland, gravity causes the mixture to crystallize unevenly as it cools, creating microscopic defects inside the glass. Those defects scatter light.
But in space.
In microgravity, it cools flawlessly, without any crystalline structure forming. Z-bland fiber optics, manufactured in space and brought back down to Earth, can transmit light signals up to 100 times more efficiently than the best terrestrial silica fibers we have today. It could revolutionize global telecommunications and internet infrastructure.
And the sources show it's not just industrial materials, it's deeply personal medicine. Companies like Varda Space Industries are heavily invested in flawless crystallization, while for pharmaceuticals.
The pharmaceutical applications are staggering. Many of our most advanced drugs are based on complex protein crystals. On Earth, gravity pulls the growing crystals down, stunting their growth and causing structural flaws. In orbit, Varda Space and others are flawlessly crystallizing pharmaceuticals.
So the drugs are actually better.
Much better. The protein crystals grow much larger and far more uniformly. This leads to drugs that are more stable, have longer shelf lives, and can be administered via simple injections rather than hours-long IV drips. Furthermore, because the crystal structure is entirely new, pharmaceutical companies can patent these space-made structures, opening up billions of dollars in new revenue.
If we step back and connect all of this, the helium-3 mining, the 3D printed lunar habitats, the orbital factories, the entire Artemis program reveals its true scale. NASA explicitly calls it the Moon to Mars architecture. The moon isn't the final destination. It is a harsh, unforgiving, 1/6 gravity proving ground for the rest of the solar system.
The moon is the ultimate stress test. Before humanity attempts a 250-day transit to Mars, a journey where there is absolutely no abort option, no quick return, and no possibility of a rescue mission, we have to know, with absolute certainty, that our survival technology works under the harshest conditions imaginable.
We have to test those small-scale nuclear waste generators and fission reactors on the lunar surface for years. We have to master large-scale cryogenic fuel storage in the orbital depots to ensure the liquid methane doesn't slowly boil off into gas over months in deep space.
Exactly. Because the margins for error change dramatically. If a nuclear reactor fails on the moon or a habitat seal degrades from dust, it is a catastrophic emergency, but it's only a 3-day trip home. You can theoretically launch a rescue.
Right, but Mars is different.
If that exact same failure happens halfway to Mars, it is a slow, fatal, highly public disaster. The moon is where we learn how to survive deep space while still keeping one hand on the railing.
So, to summarize this incredibly dense, world-shifting deep dive, we're looking at the near future right now. The upcoming Artemis missions, starting with the Artemis II crewed flyby in April 2026 with astronauts Weissman, Glover, Koch, and Hansen. They are magnificent, brave endeavors, but in the grand economic scheme, they are just the scout ships.
That's a good way to put it.
The real mission of the 2020s and 2030s is deeply aggressively industrial. The moon is effectively permanently becoming Earth's eighth continent. It is simultaneously a high-tech mining town, the solar system's only gas station, and an orbital factory, all rolled into one heavily contested sphere.
It is the foundation of a completely new economic era. The technology is being developed right now to extract helium-3, to survive the brutal lunar night, to process dirt in a vacuum. These innovations will bleed back down to Earth. They will fundamentally alter heavy industry, automation, and energy generation on our home planet.
I want you, the listener, to stop and reflect on this for a second. Think about the physical device you are using to listen to this deep dive right now. Think about the electricity powering your home grid, the complex global supply chains that deliver your food and medicine, the delicate geopolitical stability of your daily life.
It's all connected.
Exactly. For your entire life, these have been strictly terrestrial concerns. But now, as of 2026, the future stability of every single one of those things is intimately, inextricably tied to a desolate rock sitting 238,000 miles away in the dark.
The paradigm shift simply cannot be overstated. The 2026 return to the moon is not a temporary visit. It is a permanent pivot. Humanity is actively, aggressively transitioning from a fragile, earthbound species to a true interplanetary industrial civilization.
And the engine driving that massive evolutionary leap is the clean energy promise of helium-3.
It is the ultimate shift in human perspective. When we look up at the night sky, we aren't looking at poetry anymore. We're looking at our own infrastructure. We are. But this massive leap forward raises an incredibly important question, a final, lingering thought I want to leave you to mull over. We've talked about the incredible benefits. If humanity successfully transitions its global baseload power grid to rely entirely on lunar helium-3 fusion, we essentially solve the worst of climate change.
Right.
We completely eliminate our reliance on dirty fossil fuels, and we stop generating toxic radioactive waste from traditional fission. We achieve an era of abundant clean energy. But in doing so, we also create a civilization that is entirely, completely dependent on a 238,000-mile-long supply chain stretching through the lethal, unprotected vacuum of space.
Which introduces a single point of failure on a planetary scale.
Exactly. So what happens to Earth if a massive Carrington-level solar flare wipes out the orbital depots? What happens if a rogue micrometeorite strike cascades through the lunar gateway? Or, perhaps most terrifyingly, what happens if a terrestrial war spills into orbit and a cis-lunar military blockade severs that single vital umbilical cord providing our energy? When we look up at the moon, that pristine sphere turned vital industrial engine. Have we finally achieved clean energy utopia, or have we simply moved our most critical existential vulnerability into the stars?
Thank you for joining us on this deep dive.